Just waiting for it to go live. All right, looks like we're live. Awesome. Let's get started. I want to see if that's too big. I mean, I think that's too big for me to program with. There. That's pretty small. So that should be fine. Tracker. There we go. Now I want to get let's see if we can get a server started here. So welcome to the stream. Let me make sure I'm just getting things set up here. I forgot to check to make sure that the information was accurate on here. Oh yeah, there it is. Okay. Yep, working on the Zig Debugger. Let's keep doing that then. Okay. Turn this audio down. Okay. So one thing that I've done as we get started, one thing I've done since last time I streamed is I have done a bit of work. One thing is I upgraded Zig. Oh, Zig version. So I'm now working on the development form of Zig, and I usually don't. But Zig 14 or Zig 0.14 is going to come out sometime in the next 2 or 3 weeks. I think it's February 17th. And so Andrew Kelly said, hey, you should move to dev and start getting things ready. In general, he's saying that in general, to start getting ready for the 0.14 release. And so I've done that. He said it should be fairly stable. So that's what I'm working on. And one of the things is, if I look at Zig build, there is a server. Watch. Aha, yeah, continuously rebuild when source files are modified. So I kind of want to try that here. I usually use watch exec, but let's see, Zig build, let's see, summary all, and that's just watch. Yeah, it's watching 75 directories, 0 processes. If I save that, yeah, it's going to rebuild. Oh, nice. I wish it had like I wish it would clear the screen, right? Before it did that. Makes it a little easier to follow where it rebuilt things. But anyways, so that's one thing I did. Another things that I've done since going is I've kind of refactored a bit. Move the mouse out of the way there. So prior to, let's see if we go to main, yep. Yay. Yeah, okay. We don't need that right now, okay. So in main before, we had all our debugger code kind of running in this else statement. I've just added a new function called run debugger, which really does everything that we had before. Except a few additions, we'll get to those. But also I've gotten down to now, I've added a few trace functions. So if we go to the trace library, or the tracer, you can see that we have just a few nice wrapper functions for working with ptrace. one's unset breakpoint, step back, read the registers, continue, wait, and set breakpoint. And actually, I don't think unset breakpoint is, oh no, we use it. I must have, there was one I had, it was like reset breakpoint, but I was never using it. So I just deleted it for now. So that's what we're working on today. Oh, and then after that, started working on some dwarf information. So with Linux debugging, ELF is the executable format. ELF is the executable and linkable format. And then there's dwarf, which is the debug something or other or another something. I don't know. I have it up. I have it open here right here. Let's see. In fact, my mouse is super. Okay, there we go. Pin that. Dwarf. I thought it had what dwarf meant, but it's just a debugging format. Adds when you build like a debug or something with debug information. Pretty much always on Linux, it's going to be the dwarf format. Especially if you're working with ELF, dwarf is the format for ELF. So anyways, I played around with that offline because I wasn't really used to working with that information. I'm still not used to it, but I wanted to kind of get an idea of what this looks like. So my goal is, oops. Oh, no, yeah. Okay, there we are. Today, what I want to work on is getting, if I, that's not it. There it is, yeah. Is setting the breakpoint by source file and line number. So right now, we set the breakpoint by giving it the address in the executable. But that's not super helpful. So if I we play with what was it, dump read elf. Oops. I think it's the dump object dump. That's what it is. So we object dump. There we go. The file here. This is the disassembly of the text section of our test bin, right? The binary that we're using to test our debugger right now. And so really, if we want to go to main, there it is, test bin main. And you can see what the source looks like for each line. You can see that we've got the source line here. And here's a main void, and it tells you, hey, this is what's happening. And then on these lines, on const number 10, we can see that we get addresses for where these different things are happening, which is awesome, which is great. But if you want to debug, you don't really want, you want a source level debugging, not, I want to build it and then search my executable for the correct address, right? I don't even know if this is actually the third instruction in test main.bin anymore. I might just delete that. But so yeah, the way we can do that is playing around with dwarf information. So right now we have this, and I could do something like standard debug print lines. Oh no. We'll just do lines. This should build. What does it not like now? Cannot format without specifier. Oh, I think it's any. There you go, because that builds. So now if I run our, see if I do clue, so yeah, so we get a whole bunch of binary data. So that's, you know, that's awesome, but it might be better if we did dwarf. It's not gonna like that I'm not using the lines. What does it not like now? Valid format string S for type val. Okay, yeah. Where were we? Oh. Excuse me. Get that built. So yeah, you can see we have a whole bunch of dwarf functions, debug dwarf func, a lot. We get some section data and more section data. So the idea is, I think in the abbreviation table, so as I was studying this, I think it's the brief table that we might want to be interested in looking at. So let's, I thought it would be lines, but a lot of stuff was pointing at brief. So let's do abbrev. Oh, no, we can't just do that. We gotta do like this. Let's do abbrev. Yeah, debug abbrev. Abbrev. And I'm guessing this is just be a binary data again. Yeah. Lines 117, 130. Interesting. Interesting. Okay. So I think what we'll have to do is build a, I should put this as a brev, kind of a parser for it. Because I don't think I do at Zig dwarf. Zig provides some basic dwarf functionality, which we're taking advantage of here, but actually reading through the data, I don't know if it's going to have this. I hate this about the docs. It's like I have to, yeah, get dwarf, want standard debug, dwarf. And no, what's the one where you just get the type? Type. Standard built-in type. That's not what I want. So what is it with the type stuff? Looking for the comp time. Struct. Okay, so I think it is just type. Info. Do a brev. Let's just test it out. Oh, I should just do that. It's an array of constituents. So this is going to be a stream where we're reading a lot of documentation. If you don't find that interesting, I'm sorry. But feel free to ask questions about what's going on. Let's see. We're on version 5. Pretty sure that's the version that we have. It's been out since 2017 at least. Yeah, February 2017. So would not make sense to be using any other version. Let's see. Abbrev. That's strange that it's not there. Okay. Debugging information entry. These are all attributes, but I want yeah. This is the location descriptions. Debugging information must provide consumers a way to find the location of program variables, determine the bounds of dynamic arrays and strings, and possibly to find the base address of a subroutine's stack frame or the return address of a subroutine. Furthermore, to meet the needs of recent computer architectures and optimization techniques, debugging information must be able to describe the location of object whose location changes over the object's lifetime. Talks about single location descriptors. Location lists. Location lists are used in a place of location description whenever an object whose location is being described can change the location during its lifetime. So these are all different kinds of descriptions. Composite. They have location lists to use in place. Location list is indicated by location or other attribute whose value is a class lock list. Easy. Debug. Abbrev. Surprised that it's not finding. Okay. There we go. Spelling it wrong. Recodable split execute OC. Compilation unit header. Debug info section contains a reference to the debug abbrev table. Abbreviations table for the skeleton compilation unit. Each dwarf package file contains no more than one of the following sections compiled. These aren't. Full and partial compilation unit headers. So Zig is a single compilation unit language. So we should just be able to get what we want with full right now. And then maybe later supports partial, I guess, if there's linking going on. But for right now, we're just going to go with the full. Four byte or 12 byte unsigned integer representing the length. Yep. 4-byte or 8-byte unsigned offset into the debug abbreviation section. This offset associates the compilation unit a particular set of debugging information entry abbreviations. So for 4-byte, so it's a 32-bit integer or 64-bit, depending on your architecture. Each debugging information entry begins with an unsigned LEB 128 number containing the abbreviation code for the entry. Okay, abbreviation. Aha. The abbreviation tables for all compilation units are contained in separate object files section called debug abbrev. As mentioned before, multiple compilation units may share the same abbreviation table. Abbreviation table for a single compilation unit consists of a series of abbreviation declarations. Each declaration specifies the tag and attributes for a particular form of debugging information entry. Each declaration begins with an unsigned, let's see, Little Indian, I forget what the B stands for, but it's 128 bits. 128 bit number representing the abbreviation code itself. It is this code that appears at the beginning of a debugging information entry in the debug info section. As described above, the abbreviation code 0 is reserved for null debugging information entries. Wait. And is the code that appears at the beginning of debugging? In the debug info section. As described, the abbreviation code is followed by another unsigned LEB 128 number that encodes the entry's tag, the encoding for the tag name given here. So you have a bunch of tags, and there's the values. I think those tags are actually in. So if we go back to a standard dwarf, I think, where is dwarf? There it is. Yeah, dwarf tag. Interesting. Let's take a look. See if we can find array type. Array type 1. So yeah, that's interesting. They're in here. Are these all the same? 8, 7, 6, 7, 8 tag import declaration. Import declaration. Okay, so these are the same. I'm gonna guess. Dwarf 5, high user. Oops. Yeah. Very cool. Following the tag encoding is a 1-byte value that determines whether a debugging information entry using this abbreviation has a child entries or not. The debugging value is DW_children, yes. The next physically succeeding entry of a debugging information entry using the abbreviation is the first child of the entry. The 1-byte value following the abbreviation tag encoding is no. The next physically succeeding entry in the debugging information entry is the sibling. Okay, that's cool. Either the first child or sibling entries may be null entries. So let's play around with the parsing this debug information here. What we'll do is we're gonna make a new file here. We're gonna go source. We'll call it a dwarf. Dwarf that's it for right now. Tools for parsing dwarf data. Okay. Okay. So we do like function, parse, brev, table. So let's just check, see if Zig, I don't think it had that there. Helps if I spell table right. Let's just do the brev right now. Dwarf brev code. Oh, it does. Implements parsing, decoding, and caching dwarf information. A rev table list, empty, filled by the initializer. So if I, interesting, so see, this is why it's good to read the docs on everything. So if we come back up here, get that out of the way. Instead of this, we do a brev table list. Now what do we get when we get it? Yes, yes. We get unmanaged array list of brev tables. The items, we have table offset 0, brevs, offset 98, brevs. There's only 2. Interesting. Oh, you know what? It'd be cool too if I had a notification so you could see if it passed or not. That's one thing I liked with watching Zach, is I could get notifications. Let's do this. For brev in, I mess this up all the time, for dwarf dot brev table list. See, look at that. Okay. There's a lot of information in here. You get the first table, quite large, and it has an offset 0, and then we get abbreviations. Yeah, abbreviation 1. Okay, let's just parse this. Let's have this be nice and clean here. For, let's see, a ab in, oh, I messed this up. It's been writing too much Python lately. A lot of data. Here we are. Okay. So we get Brave as a code, as children, as attributes. So several attributes, a rev attribute, ID, form the payload 0. So let's take a look at what this looks like. I go to a brev as attribute, and these attributes are U64, U64, I64. What do these attributes mean? What do they mean? I bet they are in this, not here, but in, oh no, they're not. Say this, oh, here's the attributes. I go source, sibling location name. We want, like, if we got an attribute 2, here's an attribute with ID 2, form ID is 24. In hex is going to be, let's see, 16 plus 10. So, let's see, no, 16 plus 8 is going to be 18 here. Expression location. Okay. So we're right here, form ID, payload 0. This is interesting. So let's go back to here. Oh, hey. Yeah, Python syntax. Too much Python these days. How's it going, Eli? Or is it Ellie? Eli? So come here. So each debug attribute, now attribute encodings. The encodings for the attribute names are given here. Sibling, location. See, we're geniuses. We figured this out. Ordering. Classes and forms. Each class is a set of forms which have related representations in which are given a common interpretation according to the attribute in which the form is used. Not gonna lie, that made no sense. How you doing, Saeed? Let's see. Attribute form governs how the values of an attribute is encoded. The class and the forms they include are listed below. Form dwarf form section offset is a member of more than one class, namely address pointer, line pointer, location list pointer, MAC pointer, range list pointer, string offset pointer. As a result, it is not possible for an attribute to allow more than one of these classes. The list of classes allowed by the applicable attribute in table 7.5 on page 207 determines the class of the form. I have to read that through a couple times. In the form descriptions that follow, some forms are said to depend on part of the value of the attribute of the associated compilation unit. In the case of a split dwarf object file, associated compilation unit is a skeleton compilation unit according to otherwise associated compilation unit is a containing unit. Each possible form belongs to one or more of the following classes. No, that's not what I wanted. Crap. You're in chapter 7. Those three. Yeah, we were just, yeah, there are abbreviations tables. Okay. Typed it wrong. So here we were. Oh, oops, I skipped past all these classes. Okay, so here's the classes. So a way to like go back if I click this. Okay, let's take a look at these classes. Attribute value forms belong to one of the classes shown in table 2.3. Address refers to some location, address pointer, block. An Explock is a dwarf expression for a value or location in the address space of the described program. A leading unsigned LEB 128 value specifies the number of bytes in the expression. Interesting. Okay. I hit back. Nope. Let's go back to where we were. There we go. So we have an object of appropriate size to hold an address on the target machine. Okay. The size is encoded in the compilation unit header. Indirect index into table of addresses as described in the previous bullet in the debug address section. So we have dwarf form address X, dwarf form address X1, dwarf form address X2, dwarf form address X3, and dwarf form address X4. The representation of dwarf form address X value is the unsigned LEB 128. Forms of these other ones are a 1, 2, 3, or 4 byte unsigned integer value, respectively, which is similarly interpreted. The index is relative to the value of the dwarf address. So let's take a look, because we have one that we've identified here in this first part here. In fact, let's just print this off here. Just doing lots of fours. We're just exploring around here now. For ab.adders. If adder dot d equals, and it's standard dot dwarf dot at dot what is it, number 2? Location. This will print us all our location attributes here. Aha. So look at that. We have a bunch of null payloads, and we have these like, oh, these ones here. So the exact same value. Interesting. Okay. We have different forms, 24, 23, 24, 23, 24, 23. So let's take what 24 and 23 are. It should be 18 and 17. Oh, I gotta go back to the form. 18 and 17, a section offset or an explore location. Well, I'm learning it too, so we're just learning together. Is it Cremo? Yeah, it's a bit of sorcery, that's for sure, but it's fun. Now, if you've got questions, I'm free to explain things as much as I can. Some of it I'm still learning, right? That's why we're doing this 444 if horrendous stuff right here, because I'm just trying to figure out what we're playing around with. So we go back to the documentation. It says we'll have an expression location and let's see, a section location where let's look at expression location right now. This is an unsigned length followed by the number of information bytes specified by the length. Interesting. Well, I do remember reading somewhere like if sometimes they're null, which we have here, a bunch of null ones, and that could just mean that it's something that exists only in the compilation. Like once it's compiled, it kind of gets, so these could be constants that are gotten rid of. Yeah, you know that series when the docs have line numbers on them. Let's play around with one of these. This one right here. It's 24. And it's got a payload of this ginormous number, which is an unsigned 128 length LEB. So LEB is a little Indian something 128. They define it here. Wish I could like, is there a bookmark place? I'm not used to using this. It's like bookmark where I'm at. Come back to here. Okay, page 214. Remember that. LEB 128, and it's going to be everywhere. So algorithm to decode an unsigned LEB 128 integer. Well, that's nice. They just give us an algorithm here. Let's write that up. You're thinking about picking Zig, having imposter syndrome from coding, and I don't know what Apex is, but I'm sorry that you're feeling imposter syndrome. And now I kind of want to look at programming Apex. Programming. It's Apex. Apex strongly typed object-oriented language that runs on Salesforce servers. Okay, Salesforce stuff. That's cool. Well, Zig is fun. I wish I could do it at work. I do a lot of Python at work. Pretty much all Python or SQL. So when I get a chance to program in Zig, I find it a lot of fun. It's just simple, but low level. Have you done anything like C or anything else like that? Yeah. I know a lot of people don't like this style. Some of this, I don't know. When you say like the style syntax, are you saying like the actual syntax was different, or are you saying that you wish like Zig formatted it differently? Okay, yeah. So then, yeah, if you've done some C and some Pascal, um, then the syntax and that kind of stuff should be pretty easy to understand. And really, I think maybe the hardest thing for people coming, I don't know, I don't know, is like working with allocators and picking the right allocator, because with Zig, there's just so many choices that it can be a little overwhelming. Particularly if you're like me, I came from a Python background and had done a little bit of Rust, but in Rust you don't pick an allocator either. And so learning about those allocators, it was a little I don't know, a little intimidating at first, but once you learned it, it's like, okay, this isn't so bad. So Eli, what's my use case for using Zig? For fun. That's my use case. I think it's just fun to program and I want to learn Zig. The loops and the dot star on the, okay, yeah, I can get that. Or the dereferences, and yeah, there's a lot of anonymous structs everywhere. Yeah, I could see that. It's definitely a syntax that looks different at first, for sure. The for loops, I've actually gotten to used to actually kind of liking them, other than as you've seen before. Excuse me. I still like to do my for object in object from Python. Okay, we're gonna skip this function here because we don't need to parse the abbreviation table. What we do want is a decode LEB 128, and it's gonna take I think it needs to take an array of U8s. We'll think about that for a second, and it's going to return a usize, or actually unsigned. Ugh. Unsigned. And here's the algorithm they have here. It says result 0, shift 0 while true. So result var result equals 0, var shift equals 0. There we go. While true, what are they doing? They're taking a byte as the next byte and input. Result is the low order 7 bits of the byte shifted. Yeah. Let's see, var byte maybe equals, actually probably just const. Equals, oh, we need to name our stuff. Let's call this input. Input 0. So really, what we want is var I equals 0. And then we want to do I plus 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 equals 1. Yes, oh man, I worked at a place I was doing like debugging stored procedures in SQL, and the database had 2 versions of the way you could spell, I think, what was it? It was like custom or something like that. It was misspelt in half the tables and spelt correctly in the other half. it was kind of funny. I know it drove a lot of people crazy, but they just couldn't fix it. Guess that's why it's good to get second check on things. Okay, next byte and input. We do const, see. Result, let's see, or equals low order 7 bits of the byte. Shift. Yeah, okay, I've done this kind of algorithm before. It's a way of encoding. It's like a flexible way to encode long numbers, so you don't have to, like, if you want to do 128-bit number, but a lot of them might be 1 or 2 or 3. You don't want to have 16 bytes wasted of zeros. And so it's a, what's another one? What's the other term I've heard for it called? Oh, I can't remember. What was it called? I know that Go uses them. I'm pretty sure. High order low bit. Low order 7 bits. So we want to mask out 1 byte and 0, 1, 0, 1, 1, 1, 1, 1, 3, 4. Okay. And then shifted by shift. Just to make sure I've got the ordering there. And then semicolon. If high order byte. So if byte and see, it should be 0x1 0 0 0 0 0. Okay, there we go. Yeah. And that is equal to then break. Oh wait. Equals 0. Silly me. Oh, put the parenthesis on the wrong side there. Found equals. Expected block or assignment found equals. Really? Oh, that is what is wrong. How did I get into Zig? I just decided I want to learn another language. I kind of was tired of Rust. Rust is a great language, but I just was had I got a little frustrated with the foundation and some of the things that they're trying to do, and so I decided I want to try a different language. I did Odin a little bit. It was just the compiler was a little too unstable at the time for me. And so I started doing Zig because I had seen a lot of people talk about it, started working on it. And then really what helped a lot was getting on Zigit and talking on there and just reading through that, and decided to do some fun toy projects in there and just really started to enjoy it. Yeah, I think Odin has some future growth for sure. When I did the little bit of Odin I said it's like Go if Go had made a few more what I would consider reasonable decisions. It has a lot of nice things around, like so like Go with error handling, it's all the null checks and all that, and that's fine. I've written some Go and it's okay. But Odin is like the exact same syntax as Go, but has a lot of like, it has some nice features around dealing with those error checks and like results, and not having to deal with always checking null, because that is the worst thing about writing Go for me, is just remembering to always write the if nil. if result is nil, then do the error handling. And partly because you have to do the same thing in Zig in a way, right? You're always checking if a function fails, you always have to do something about it. But that's, the compiler forces you to do it, whereas Go doesn't force you to do it. It just breaks, or even worse, doesn't break if you don't check. If you're starting learning Zig, I don't know, what are you interested in? Like, what kind of things are you interested in doing? My first project, like, we go to GitHub. We go to my repositories. My first project, I was thinking about this earlier, in Go, or not Go, in Zig, was VT parse. And all I did was I was playing around. I was interested in terminals and how they, like, the VT parsing escape sequences and those kind of command line stuff. And so I was reading about VT parse, which is this is just a reference implementation in a way. Is it not even a reference implementation? It's an example implementation of the DEC compatible state machine parser. And so it's all in C, except for there's these like Ruby things here that generate C files. If you like, when you read through it, you're like, oh, this is just generating a C file. And so what I did is I just converted this into a Zig implementation, and instead of using Ruby, used comp time, which I thought was a fun way to learn comp time. So I think what's important is it's a project that you're interested in, and that isn't so hard that you're learning something new at the same time, if that makes sense. Like, so if you've never written a database, I don't think writing a full-on database is necessarily a good idea to do that, or something like that. But I also don't think that you should go short. That's more, especially like for languages like Rust, I think that advice really sticks, because Rust is quite difficult to get used to. Zig, I think it's less so, because Zig is pretty simple, that you could learn Zig pretty fast and then say, okay, I want to try something that I don't know how to do, but I think I could figure out in Zig, because it's, like I said, it's pretty simple. You could learn the syntax and everything within like a day or two. It's then kind of learning there's a few hard edge cases that can get you, but I think those are the things you won't run into till you start doing something that challenges you a little bit. So I don't know. That's probably, I'm not good at advice, but that's kind of my thoughts on that. It would be, what are you interested in doing, and then doing something like that, and not being too worried about it's been done before, because it doesn't need to be perfect. It doesn't need to be, this is a learning project. It doesn't need to be something that blows up on Hacker News or anything like that. Just be like, hey, I wrote this because I want to learn how, like this, right? I want to learn how debuggers work, so that's why I'm writing a debugger. So I was going to show up my second big Zig project, because that first one wasn't really that big. As I thought I wanted to write a TUI, like a Z2E thing, and anyways, I ended up implementing the key, like a keyboard event handler for here it is, Tabby. Cool. Yeah, hopefully that's good advice, and it's fun. I think if it's fun, you're gonna stick at it, right? And so, and what's cool about Zig is that if you find like a tutorial, not that everything you want to do is tutorial, but if you find some, like what we're looking at here, right? This is all C. Well, this is even C. This is pseudocode, but it's pretty easy to translate between C stuff and other things. So Yeah, you could check them repos. They're not, the greatest, but that's stuff. Other things like on the line of learning about Zig, if you want to learn how to like write more Zig, reading the standard library is also good. In fact, that's what my next video on the Zig for uninitiated is probably going to be talking about stuff I've learned from reading the standard library code for the general purpose allocator, because it's actually quite interesting how they implement it. It's not the same as it's not what I expected. Okay, so this should then, what's it? Oh, shift plus equals 7. Yes, and result needs to be, since the U size, this needs to actually, it should be a U128, and this should be what's log 2 of 128.64. Thanks. No, thanks for watching those videos. And saying those things. Just when people say nice things, it just makes me feel good. So thank you. Okay, let's add some tests here. Let's test this out. Decode. So if we had I thought I had seen some references like in the documentation to give us some examples so we can test. Let's do input const input equals U8. Let's see, I'd seen examples of unsigned little engine encodings. Here we go. So let's just test to make sure our encoder here works. There should be no second byte. And we should get tests. Let's see. Decode. Const. Let's see. Testing equals standard.testing. What we want to do is the testing dot assert expect equal value should be 2. Our input ref input. There we go. Let's test that out. Zig test summary equals all source /dwarf.zig. Oh, build. Oh, I hate this. This is one thing that's annoying about Zig a little, in my opinion, but testing, test, ref all decals. Let's do import dwarf equals dwarf.zig. Yeah. Oh, by the way, is this easy to read? I'm trying to make sure that it's not. At ref, oh, let's see. It looks great, okay. Thanks. Zig ref all decals. Did they already get rid of it? Oh, testing ref all decals. It's a function in testing, okay. Standard.testing.ref all decals. There we go. So now we got an error, which is good. Let's see, cast discards, const qualifier expected. Oh yeah, okay. Okay, so the problem here is that input here is a const, and the function declares that it needs to be variable. So we can just do that, because you can always pass a variable, like a mutable value in for a const, but you can't pass a constant value in for one where it's expected to be mutable. So now I should put this on watch. Watch -e zig build test summary all, and I want it to notify me. Oh, there we go. And exited. Var needs to be usize. It's fine. You'd see type U8 cannot represent integer value 17.8. Interesting. It is a U8. This should be a U8 as well. Yeah. Is it complaining? Let's see, const low bits equals. Is it this that it's mad about? No, it's still mad about this. Byte. And oh, geez. There's the problem. Expected type U3 found U64. Guess how many times do we want to shift? Oh, because we're shifting a byte. But on 128, it could. $64. I guess, yeah, we only want to shift. How many? 128 is a number that can be done in U. Oh, is there another 0x? Oh, yeah, thanks for catching that. So this is a good thing to learn about here in Zig. So I'm gonna pull up the docs here. So in Zig, if we go to operators, operator. Okay, I'm gonna put music on. My music stopped. and I want music. Okay. Sorry, you can't listen to music because it's on YouTube, and I don't want to. I want to steer clear of the YouTube copyright stuff. So, where are the operators at? Operators. So you look at the table operators. When you do a bit shift, this is a very common thing when I see on like people asking what's going on. It's fine. Here it is, bit shift. So here we're shifting left. It moves all the bits to the left, inserting new zeros at the leading significant bit. So what we're doing here is, and I guess I should walk through why we're doing this, but we're taking the lower order 7 bits of this byte, and we want to shift it onto the result. And every byte in this array, the only thing we're interested about, the only ones are the first 7 bits. And the last bit is just a continuation bit, the highest bit. If it's 1, that means the next byte is still part of this number. So we're interpreting this number byte by byte. And then once we get to that final byte, we can say, okay, we're done. And we'll get a number out. Now, when you shift these bits, to be safe, you have to be able to, we have to know what the size of the shift is, or else we might overshift the these bytes, and then we lose some because, you know, if result's 128 bits long, whoops, and if we shifted 200 bytes, then we'd lose all our data, right? Or 130 bytes, we'd lose, not bytes, 130 bits. Then all our data would be lost because it would just be zeros. And so you probably don't want that to be what, that's probably not what you want. And so Zig, with the operator, requires that B be comp type known, or have a type that is log2 the number of bits of A. And so there is some nice stuff for doing this. So you can do like, I think it's standard.math.log2 int turns log base 2 of integer log x. Well, I want the type. There's like a type function for the standard.math.log. Oh, no. But it's log2 of 8, basically. So, which would be 3? Yes. Because we're shifting a bit, bytes, onto result, when it results 128. So we should be able to shift it. Oh, that's right. So at this point, we need low order bytes to be, that's right. Okay. Sorry, I'm jumping all over the place here. So if I'm confusing you, I'll try to slow down here. So U64, that should be log2 of 128. That's half of 128. No. That's log base 2 of 128. Let's see, BC-L log 128. Four, 7, okay. No. Yeah, you're right. It is 7. To the 7th. Okay, so this needs to be at least at most a U7. There we go. Now it's still going to be mad because at 1 I made a mistake there. Still going to be mad. Because it's saying, hey, it's expecting a U3 and it found a U8. And that's because low order bits is just 1 byte. It is well, it comes from here as a U8. We can say this is a U8. Right? It's a U8. But a U8 isn't big enough to hold, or rather, a U8 isn't big enough to be shifted as much as a U7 can shift you. Because U7 could shift 128 times. And that's, U8 isn't big enough to shift that many times. So what we need to do is cast this into as U60, U128, like that. That should do it. Let's see, function with non-void return type implicitly returns. Oh, so it does. Return result. And it does not need to have an error. Error union is ignored. I always forget this when you're testing. It's a error union. That comes back. There we go. So now that is correct. So now we've got that LEB parser done. Let's go back in here at our dwarf debug table here. And there's a bunch of examples of unsigned LEBs here. Oh. So we're gonna take a look at this, and we're gonna take these examples and add a test. So what I'm gonna do is add a function called test, let's see, fn test decode LEB 128 unsigned test. And what it does is basically this. But instead of that, it's going to take an input, which is an array of U8s, and it's have a U128 as its expected output. Expected. And yes, that's what we want. And this will be a void. Errorable void. Unused function parameter expected. So yeah, what we'll then do is replace this with expected and di parentheses, di w di parenthesis. Oh man, I'm really messing that up. Fat fingering it all. So now what we can do is, instead of this, we can do is the typo unsigned. Did I make a typo somewhere? Oh yeah, I did. Let's do this. Yank. No, it's not deliberate. It's that I'm very bad at spelling. Decode LEB 128 unsigned. There we go. Unsynced. Unsigned. Thank you. I would have never caught that. Okay. Where were we? Oh yes. So I was going to take this as this. So this is a recommended way for kind of doing multiple, kind of like table testing in Go, or just parameterized testing in a way. Is that you make a function that takes in the inputs and casts out the outputs. expected a U8, a variable U8, const 1. Yeah, I thought I could just const that pointer to, oh, did I? I don't think it's gonna like that either. Yeah. Okay, it liked that. Okay. That was that old constant in var. I'm passing a constant value in, and it needs to be there. Okay, so now I can do, then I can add multiple of these examples where 127, 27, and yep, successful. So let's take a look at these. There we are. So the first byte is 127 plus 0x80. You think? So because they're saying, hey, it's 127 plus the 0. That last bit needs to be flagged open. So if you add these together, you'll get the right number, and the value is, and then the second byte is 0. That should also be 127. Okay, so there's multiple ways to represent 127 with this format. Oh no, whoops, I'm looking at the wrong. I'm looking at this should not probably work. Because I'm looking at the wrong table here. Should be looking at this one, 128. Is the same as 0 plus 0x80. And the second byte is a 1. This is 128. And then let's try this one. 57. And 100 in the second is going to be 128.57. That's ironic. Okay. I think we've got a good algorithm for decoding these right now. Or we've got the code working correctly. Page 112 is where we're at. 212. Page 112? No, page 212. Yes, that's where we were. So when we were looking at the expression list, yes, this is an unsigned 128 LEB length followed by the number of information bytes. Let's now use this function to do the const dwarf equals at import dwarf.zig, and see, this is now gonna get mad here, so we're at the dwarf underscore. Yeah, it should fail to build now. What is it not liking? Local constant shadows. Declaration of dwarf. Where is that? Main Zig 168. 168. That fixes that. So come back up here. And if we standard dwarf attribute, we looked at this, it was the payload, right? Because we know this is a, yep. So then the payload here is what we're looking for. I'm pretty sure. So we want to do this. See, payload equals let's keep that there, and then we can do payload equals it should be dwarf dot, oh, probably make this a public function so we can use it. Decode unsigned adder.payload. That's an I64. That's not right. Unless I have to interpret it as a series of bytes, which we could do. But that is not enough. Right, so we were here, classes and forms. Because what we've done is we've looked at the tag. Now at the tag, we go to the attribute encodings. And we see this as, an X per lock or location list. Because we see its location as these two classes. Okay, yep, 2. And then you get a here. So we're getting these. No, that's not what we're getting. We're getting this. Oh, no. The wrong spot. Then we get some things about what kind of class it is. The list of classes applicable are on page 207. So I go back here to 207. Oh, okay, yeah, that's applicable, but the numbers are elsewhere. The values for those numbers. Okay. Form address, size, encode and unit header. This is an unsigned. So yeah, the payload. This is where it's unsigned 128-bit integer. We're getting a 64-bit signed integer. which I guess could be interpreted as, no, as, yeah, it could be interpreted as 128 unsigned. Huh. I'm gonna have to look at what's going on with the parsing code here. Let's take a look at, this is by the initializer. Okay. Load elf, load, okay, nope. Load elf, we get XZ directory number, and then load path. It's gonna load the elf in here, which then I think should call the dwarf. So it gets open. Yeah, dwarf open. So it's going to scan all functions, scan all compile units, which is what we're looking at. Brev table. Try get a brev table. And so it gets an already existing abbreviation table given the offset or not found. Items if table offset equals brief offset return table. Otherwise, we're going to append to the list with allocator parse a brev table. Here we're getting into it. So yeah, here is read unsigned leb. Look, they've already got this function right here. Probably didn't need to write this. Fixed buffer reader. Huh. Interesting. Okay, true code has children, while true, it's going to read through all the attributes and the form IDs. If attribute is 0, form ID is 0, it's the null one, it breaks. Otherwise, try append to the attributes ID form payload, which is you take the form ID and form implicit const. We're just reading about implicit const. Implicit. I've just seen it in reference to here. For attributes of this form, the attribute specification contains a third part, which is assigned 128 number. The value of this number is used as the value of the attribute, and no value is stored in the debug info section. Okay. It's weird. Because according to this, then, the only value of the payload is if form ID is this, then we're going to get that. Otherwise, we're at undefined data. which I think is interesting. I'm not sure why it only why the dwarf data only reads for implicit const. It's interesting. Interesting. I'm going to have to investigate that further. I do have to run though. So thanks for watching, everyone. It's been great. I've been having fun. Have a good one. See ya.